Welcome to TD Physics. Thank you for joining me. Today we're going to be looking at displacement and vector addition. The context of today's history story comes from Vimy Ridge in northern France, a place I got to visit with students in 2018. So why do you want to learn about vector addition? What applications can there be? Well, the Canadian engineers who served there spent a lot of time adding up vectors underneath this ridge. The memorial itself sits atop a modest ridge which commands a good view of the area to the east and to the south. The British and French had struggled to displace the Germans for many attempts. This is a small town that's about 2 kilometers away. Here's a shot with a telephoto lens. This was the nearest help that soldiers could hope for when they assaulted the ridge in April of 1917. They bunkered down in deep trenches to protect them from shell fire. And today, if you visit, there are many warning signs that keep you out of the region, lest you go up like one of the grass-cutting goats every once in a while. And so these deep trenches, the engineers would start digging underneath enemy lines very, very silently, load them full of explosives, and then at the appointed time, launch them off before an infantry attack. Even today, the ground is again too dangerous to explore and magnificently cratered all around the region. So today's soldier that we're going to talk about would have been hiding out in those trenches, and the rank of this soldier, Spr Gilmore, sapper meant that they were an engineer, and he was part of the Canadian Corps of Engineers associated with the 66th Battalion. Sappers were commissioned officers, which meant that they were fairly high up the ranks. This actually rankled some of the other kind of old guard upper ranks in that many of the sappers were recruited from the working class, such as diggers for sewer systems or perhaps subways and the like. And so it kind of upset the class as they understood it at the time. Our soldier we honor today, his name is Stanley Gilmore. And he was an American who fought for Canada, for the British Empire. He was born in Kansas, and his mom, at least at the time of enlistment, was from North Dakota. He ultimately enlists in a prairie or a western battalion. So remember that Canada has barely had the prairie provinces join at this point. His career at that point, he was a blacksmith. So remember that was working class, and the high-ranking soldiers did not like saluting a blacksmith by any stretch of the imagination. And so as we head down a little bit further, we learn that he was about 5'9". His complexion was swarthy, which means kind of darker. Eyes were brown, hair was black. He had some scars. And so that was his background. And while he was serving at Vimy and was responsible for digging some of those trenches and setting some of those mines, later on in the Battle of Passchendaele, he ended up receiving a pretty serious shrapnel wound. It looks like a shell must have gone off very close to him. So he got to France in 1916, returns to England with some serious wounds, and notice that he doesn't get back to Canada until 1919. So it took a while to give a little sense of how horrible war can be, especially in World War I. This is his casualty sheet. And so this would be gunshot wound or just shrapnel wounds to legs, his left hand, and his thigh, and his ankle. And we get a bit more into some of these details. Apologies to those who didn't take cursive writing, especially doctor cursive writing in elementary school. Multiple shell wounds. Right leg. And so he's got a grazed wound on the inner side of his leg, and then some pieces are missing from the original. And so we've got a piece of his tibia that's going to be broken up, and that's kind of nasty. And so he also gets one in the leg, and then he also gets one in the thigh, and he also gets one. Here we go. Wound in groin. Just not good. And then one of the things that's found repeatedly here enters the pubis, that's the big pelvis bone, and dirty wound is repeated in here as well. So you really, really didn't want to have shrapnel explosions and the grime of war splattered all into your wounds. He was an engineer who had to come home the slow way at this point. In the end, Spr Gilmore returned to Canada, and he lived to the ripe old age of about 74. But what does this have to do with vectors and adding them? Well, the sappers, when they were digging these tunnels or their trenches, it was important that they put little dog legs in them so that they would change directions, lest someone infiltrate and be able to wipe out the entire tunnel at once, or should there be an explosion. This would help mitigate the disaster. And using scale diagrams and adding those individual displacements as vectors were a key way of keeping track of where you were. So, some physics vocabulary. A scalar is a physical quantity that has only a magnitude or a size, and so examples of units for that would be like meters, or things like meters per second, or kilometers per hour, or you might even have units of force like a newton, or acceleration, which would be meters per second. That's a change of velocity over time. But when you add that with a direction, then it becomes what we call a vector. So this would be, say, 12 meters north, or 15 meters per second south, 12 degrees east. When we combine both our magnitude and our direction, so magnitude in units plus direction, those two combined create something known as a vector. And you can add vectors together. And displacement ones are probably the simplest ones to work with. So that's where we're going to start. One quick thing, distance versus displacement. Physics uses very specific language, and it's important that we are used to it. So if someone was, say, playing football, of course not all examples in physics have to involve conflict, or at least deadly conflict. So if we had a football player and they started on their own 40-yard line and they dropped back a little bit and they went over and then they ran down the field, well, our total distance would be, well, we'd be going back 5 and then across about 10. And then we'd be running up from our own 35 up to their 30. And so that would be 10, 20, 30, 35. And so our distance in this case would be the sum of all those together. So that'd be about 50. We'll assume that these are yards. So some American units here for fun. But our displacement in this case is how far did you manage to get away from your original spot. Our displacement in this case, and so our displacement in this case, if we were starting on our own 40th, our displacement only would consider how far do we manage to make it away from our original spot. And so this would be down the field and a few degrees to the left, and we'd measure how long that red line was to figure out how great our displacement was. How far did we get away from the original location? So, using scale diagrams is a low-tech, simple way to do two things. One is to communicate visually with the person who is seeing your work or marking your quizzes or tests. In that case, that would be me, to give them a quick sense of what you are trying to communicate. The second piece is that it gives you a quick sense of, does your mathematical answer, if you work on that, make sense? So here, if we have a vector, so it's a vector because we have 160 kilometers, so that's a magnitude, and east is a direction. So those things come together. If you're going to use a scale diagram, well, obviously you need a scale, and a compass rose is an essential addition as well to make sure that you're using standard assumptions of north being to the top of the page, as not all diagrams include that. So if you're going to be drawing something that is 160 kilometers east, the first thing we need to look at is that our scale here, 1 centimeter to 20 kilometers, you just have to make sure that you're comfortable going between a absolute value and its scale value. 1 centimeter is equal to 20 kilometers. We're just setting up a ratio here. Then how many centimeters, x centimeters, is going to be equal to 160 kilometers. So this is simply a ratio that we need to rearrange. And so if this is the case, These are both equal to one another. So if we're going to set this up, we need to do some cross multiplying here. So that would come up here, and these would switch spots. So 1 centimeter times 160 kilometers is going to be equal to x centimeters. Remember that our 20 and our x, because we cross multiplied here, switch spots. That's over 20. So our kilometers are going to cancel out, and our unknown length of centimeters is going to be equal to 1 centimeter times 160 over 20, and so that's going to be 8 centimeters long. And to draw this out diagrammatically, I would simply take a ruler and I would measure out 8 centimeters. Now this is not going to measure exactly the same as it would in your case, because I'm not sure what your screen size is, but on mine, I'd be measuring that out to be 8 centimeters, and that's going to be approximately this long. Okay, and so that diagram right here represents 160 kilometers east using this scale. So we've got a couple more examples to do like that, and then we'll work on adding some vectors. So we have one more, just simply working on scale. So if 1 centimeter is equal to 10 kilometers, and this is going to be 55 kilometers, well, that's going to be a tidier one, because 1 centimeter to 10 is going to be equal to x centimeters is equal to 55 kilometers. So again, if we set up our ratio right here and switch spots, x centimeters is going to be equal to 1 times 55, and that is going to be divided by 10. And so x centimeters, our unknown, is simply going to be equal to 5.5 centimeters. And now we have to figure out what direction it would be. So I've got a plastic protractor that you can't see right here. So basically I'm just going to have to do my best. Okay, I'm going to move that a little bit higher so I have a bit more space to draw. My vector is going to start here at the base, and we're going to start drawing east 60 degrees south. So this is a little bit unconventional. So if that was south, be somewhere in this ballpark right here. Okay, so again, measuring that this would be 60 degrees south. And the length of this line was 5.5 centimeters. So again, it may not line up perfectly on your screen because ours have slightly different sizes and resolutions, but it's approximately that if you measured it out on your sheet of paper. Okay, so yours may not be exactly the same. Please make sure you measure yours with a ruler. And then one final one here. So if 1 centimeter is equal to blank kilometers, we'd have to choose one. And so I want to make sure that it's big enough I can see it, but not so large that it runs off the page. So I'm going to choose 1 centimeter is equal to 50 kilometers. So that means if I'm looking at 150, what is x? I presume that you can see that that is a ratio of 3. So I'm just going to skip doing this math. You don't have to show this work. This is just reminding you how ratios work. So if that is a ratio of 3, that means x, the length of our vector line for our scale here, will be equal to 3 centimeters. And it's going to be north 50 degrees west. So I head back over here. So this is north. And then we're going to go all the way 50 degrees west. So over here, about in that ballpark. And I'm going to measure this line to be 3 centimeters, which is a bit shorter than what I have right here. So it'll be somewhere in there-ish region. Okay, so this is 50 degrees in here. That would be 3 centimeters long. That's how to draw a scale diagram for one vector. So what do we do when we have more than one? Well, I'm going to leave this one for your own practice, and we're going to skip off to vector addition. So when we're adding vectors, you'll notice that we have an end that doesn't have a tip and one that does. The base or the tail of the vector is where something would have started from, and the tip is in the direction that it is going. We're going to do a simple version of a student walking 4 kilometers east and then 3 kilometers south. In that case, a scale of 1 centimeter to 1 kilometer makes things pretty simple. So that's going to be 4 centimeters east. This is going to be equal to 3 centimeters south. And this will be a nice right angle triangle, so hopefully we'll be able to figure this out fairly quickly. So what is that addition going to look like? Well, we're going to start off with our 4 centimeter line going east. So I'm setting up a starting point right here. And I'm going to make that 4 centimeters long, again on my screen right here. And so it's approximately 4 centimeters. My next one is 3 centimeters south. I'm going to add the tail of my second vector to the head of my first, and this one's only 3 centimeters down. So I've added the second vector to the first. Another way of writing this would be that our total change of displacement, sometimes we throw a little arrow on top of it to remind us that it's a vector, is going to be the sum of displacement A and the sum of displacement B. I'm going to make a dotted vector to represent this. And so I need to measure this. And so if I put a ruler on this and measure it, I can also notice that this is one of the special triangles. It's a 3, 4, 5 triangle. And so this is going to be 5 centimeters long. This is my length. And now I can measure my angle from a couple of different spots, but I prefer to measure mine from south. So if I measure my angle from here, that's going to be approximately 54 degrees or so. And then what we end up with is a final conclusion that our total displacement for this system, how far did they get away from the original spot? Well, back into our scale would be 5 kilometers south, 54 degrees towards east. And there's the whole page now visible. Sorry about that. Pause as long as you need to. Carrying on. Okay, this time I'll make sure I record the entire screen. So our last question. So if we have something that's not nice and tidy and along the cardinal axes, let's see what we have. So if we are walking 2 different displacements, so 5 kilometers south, well, that's pretty simple. A 1-to-1 scale means that we have simply every kilometer is equal to a centimeter. So that's equal to 5 centimeters. That's easy. That's 7 centimeters. That's also easy. The direction will just be trickier. So we want to make sure our first line here, our first vector, is going to be, there we go. So again, our scales may be slightly different on your screen versus mine. And so there is my first one. That is on my screen 5 centimeters long. And so my next one is going to have to be 7 centimeters long. It's going to be a bit longer. And on this system, it's a little bit trickier to get it to go without slipping, but here we go. That went better. So south, and then I have to go a whole 30 degrees this way. And now I have to get the length of that right. So getting those together on this system is a bit tricky. So it's something like that. And then, of course, the sum of them together, I'm going to go with my dotted line again, is going to be from the tail of my first vector to the head of my final vector. And so this side is 5, this side is 7. So we know that this angle right here was 30 degrees. And if you want to get into some fancy trigonometry, we could use sine and cosine laws on this. But otherwise, I'm just going to measure it. And so if I measure this length from here to here-ish, that length is approximately about 11.5 or so. Officially, the pure math way says 11.6 centimeters, so I'm going to cheat and use that. So that would officially go into this spot right here at 11.6 kilometers. And my direction, I'm starting off south, going towards the east, and now I'm putting a plastic protractor on here and measuring it. And it's coming out at about 17 degrees. So I'm sure with pure math we could get a decimal in there. But in terms of a practical scale diagram, plus or minus a degree is pretty good. So our final displacement, 11.6 kilometers from where we started, south 17 degrees east. Our distance, so if you were wearing a pedometer to measure your total distance, would be 12 kilometers total, because that's simply adding them together. Notice that there's no direction here. Okay, Okay, so distance would be 12 kilometers walked, but how far you got away, or if you were calling out artillery or something, as the crow flies, would be 11.6 kilometers. I'm going to leave you with another application from the Aussies. If you're fascinated with this, stick around. Otherwise, you got some homework to do.
In a previous lesson, you have learned how the prismatic compass is used for taking magnetic bearings and for finding direction on the ground. There are many situations on active service to which this use of the compass may be applied. For instance, here is the leading section of a strong fighting patrol operating in featureless jungle country, which we represent by this woodland. The patrol is going forward to reconnoiter the line of a river running across their front about 3/4 of a mile ahead of them. And owing to the nature of the country and the thick undergrowth, they will have to keep changing direction on the way. The film will show this operation as an exercise in the use of the compass, not as patrol instruction. The patrol is prepared to fight for information and can call for artillery support through its wireless equipment. It is necessary, therefore, that it should be able to supply the gunners with a map reference for any target observed, and to do this, the patrol must keep track of its own movement. The starting point is known to the gunners. The patrol leader is not carrying a map in case he falls into enemy hands. He is going to keep direction by compass, and has detailed one man to keep a record of their changes of direction and the distances traveled on each leg of the patrol. Here you will see them setting out on the first leg of their journey, the bearing of which has already been noted. And here you will see them changing direction at a sharp bend. You must imagine this as a jungle track with impenetrable undergrowth on each side. At this point, the patrol leader takes a fresh bearing, whilst the man makes a note of the distance they have traveled on the last straight stretch. At this point, the river appears in view on their left front and far below. They must now make their way down to its level by a devious route, and at the same time make an accurate record of their movements. The distance moved on the previous leg is again noted, and the fresh compass bearing is taken. And in due course, they arrive at the river. So far, no enemy have been encountered, but gunfire has been heard and enemy shells have passed overhead. The patrol leader observes from the cover of the undergrowth and sees flashes of gunfire from the opposite bank lower down the river. He takes the compass bearing of the gun position, 17 degrees, and estimates its distance from his own position, 700 yards. His problem is now how to get this information back to the gunners as quickly as possible, and in such a form that they will be able to deal with the enemy. He plots his compass bearings and distances on a piece of paper with his protractor, making a diagram of his route. They started off on a bearing of 85 degrees, and the distance traveled on that bearing was 240 yards. uses any convenient scale on the protractor to express the distances. Using each primary division on the top scale to represent 100 yards, he marks off the distance representing 240 yards. 40, 140, 240 yards. The bearing of the second leg was 46 degrees. Distance traveled, 320 yards. Third leg, 128 degrees. Distance, 260 yards. Fourth leg, 88 degrees. Distance, 330 yards. That brought them to the river bank. Finally, he draws his line of observation across the river. Distance, 700 yards, on the observed bearing of 17 degrees. This marks the position of the enemy gun. Now he draws a line connecting his starting point to the gun position and measures this bearing with his protractor. It is 57.5 degrees. He next measures the distance along this line using the same scale that he used for plotting the other distances, 1430 yards. Now he must convert this compass bearing of 57.5 degrees into a magnetic bearing. He knows that his compass has an error of 1 degree east of magnetic north. The magnetic bearing of the enemy gun position is therefore 58.5 degrees. And he sends a message back to the gunners. Range on enemy gun position from patrol starting point, distance 1430 yards, magnetic bearing 58.5 degrees. And after a short interval, here are the ranging shots. This is an example of a counter-battery shoot worked out by compass bearings, with the patrol leader acting as forward observation officer. By keeping a record of his bearings and the distances traveled on each bearing, he was able to work out the position of the enemy battery without the aid of a map.